Hi everyone, this is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College, Women, Nalgonda. Now I am going to present the topic electrostatics in continuation to the last two lectures. So this is BSc Physics 5th semester electromagnetism paper syllabus. The plan of my talk is electric field, the location of null point. Then we will discuss the electric dipole concept. Then after electric field strength on the axis of a dipole. Later on, electric field strength on the equatorial line of a dipole we can calculate. Then after torque acting on a electric dipole when it is placed in the uniform electric field. Lastly, we'll see the potential energy of the dipole when it is placed in the uniform electric field. Let us discuss one by one. Right. The first subtopic is electrodipole. What is meant by electric dipole? This is the combination of two equal and opposite charges, that is minus q and plus q. When they are separated by some distance, that system is called as electric dipole. The combination of two equal and opposite charges, when they are separated by some distance, say 2L, that combination is called as electric dipole. So here minus q plus q are separated by the distance 2L. Okay. Let us say this is the midpoint, then this is L, this is L. Okay. Now the dipole moment is defined as it is the product of charge and distance between these two charges. Here electric dipole moment is a vector quantity. Therefore, vectorially we write it as P bar is equal Q into 2L bar. So what is the direction of P bar? Yes. So this is the axis of dipole. The line joining minus Q and plus Q is the dipole axis. This is called dipole axis. On the dipole axis, the direction is always minus Q2 plus Q, P bar direction. Okay. So P bar is a vector quantity. It is defined as the product of charge and distance between two equal and opposite charges of the electric dipole. The direction of P bar is minus Q2 plus Q along the dipole axis. Okay. Now, how to calculate the field strength on the dipole axis? Okay. How to calculate the field strength on the axis of the dipole? So consider minus Q and plus Q, which are at the distance 2L, right? At the distance 2L. Now, so I am considering the point P here. Okay, this is the point P. So what I'm saying here in the electric dipole, minus Q plus Q are at the distance 2L. Now I have to calculate the electric field strength at this point, right? So from minus Q to this point, the distance of this point from the center of dipole, say this is R cell. This is the center of the dipole, O. Okay. Then what is the distance of point P from minus Q? That would be R plus L. R plus L is the distance of the considered point from minus Q. Then the distance of plus Q to P, this would be my R minus L. Okay, fine. We know that field strength due to the point charge Q at the distance R, E is equal 1 by 4 pi epsilon naught Q by R square. Let us apply this formula here. Here we have the minus Q and plus Q. Okay. Due to the minus Q, the field strength at this point we are writing E minus is equal to 1 by 4 pi epsilon naught Q by R plus L whole square is equation 1. Now field strength due to the plus Q at this point is given by E plus is equal 1 by 4 pi epsilon naught q by r minus L whole square. Say this is equation 2. Okay. Due to the minus q, suppose that here unit positive charge is placed. Okay, then this 1 coulomb of charge can be attracted in this direction. That means due to minus q, the field strength direction E minus is towards left side. Plus q repels unit positive charge in this direction. E plus direction is along the dipole axis right side. Okay. So here at the point P, E minus and E plus both are acting in opposite direction. Okay. When you compare these two quantities, it is very clear E plus greater than E minus. Therefore, resultant field at that point I am writing E axial equal to E plus minus E minus, greater value minus smaller value. That equals to, by substituting the values from the above two equations, Q by R minus L whole square minus 1 by 4 pi epsilon naught Q by R plus L whole square. Okay, Q by R plus L whole square. That equals to, by taking common, Q by 4 pi epsilon naught taking common, 1 by R minus L whole square minus 1 by R plus L whole square. Okay, this gives Q by, that equals to Q by 4 pi epsilon naught. It is R plus L whole square minus R minus L whole square by R square minus L square whole square. Okay. A plus B whole square minus A minus B whole square form. Then you will get Q by 4 pi epsilon naught. This value equal to 4RL by R square minus L square whole square. That equals to, you can write it as 1 by 4 pi epsilon naught Q into 2L, Q into 2L into 2R by R square minus L square whole square, R square minus L square whole square. So this is equals to, that equals to what we get, 1 by 4 pi epsilon naught, but Q into 2L is dipole moment. Then you will get 2PR by R square minus L square whole square, where P is equal Q into 2L we substitute. This is the field strength on the axial line of electric dipole. So what we get? E axial electric field strength on the axis of dipole, E axial equal 1 by 4 pi epsilon naught 2PR by R square minus L square whole square. For a short dipole, comparing to this distance R, the length or distance between minus q and plus q is very less. Then you can neglect the L square value. Therefore, in that case, the field strength, we can write the field strength E axial is equals to, what I am writing, E axial is equal 1 by 4 pi epsilon naught 2PR by R square whole square R power 4, 1 R cancel. E axial is equal 1 by 4 pi epsilon naught 2P by RQ. This is the required expression for electric field strength on the axis of dipole for a short dipole. So what is the direction of E axial bar? Yes, the direction of E axial bar, you observe this figure, due to minus q, E minus in this direction, due to the plus q in this direction. Here E plus greater than E minus. Okay, so therefore the resultant direction is towards right side, that is E plus. But the direction of dipole moment also minus q2 plus q along the dipole axis. Therefore, on axial line, on the dipole axis, the field strength E axial bar is always parallel to P bar. dipole momentum direction minus q2 plus q along the dipole axis. On the E axial bar direction also parallel to dipole axis minus q2 plus q along the dipole axis, or another, we can say in another words, E axial bar parallel to p bar. The next, let us see how to calculate the field strength on the equatorial line of your dipole. Yes, for that I am drawing the figure minus q. This is plus q, right? This is the equatorial line. L because length of the dipole is 2L. Okay. On the equatorial line, I am considering the point P at the distance r from the center of the dipole. Okay. So to calculate the field strength, just imagine that 1 coulomb charge is placed at the point P. Then this 1 coulomb charge can be attracted in this direction by minus q. So due to minus q, the field direction is like this, E1 bar. Okay. But plus q repels unit positive charge in this direction. It is E2 bar. Okay. Suppose if the angle here is theta, then this will be theta. Okay. This will be theta. So E1 bar is acting in this direction. E2 bar is acting in this direction. So two vectors are acting at some angle theta, right? Then the resultant direction would be along the diagonal. If you consider these two as adjacent sides of a parallelogram, then the diagonal passing through the same point, that represents the resultant direction. Okay. So here, if this is angle theta, then this will be theta. Then this component is what? This component would be E1 cos theta. For this E2, E1 cos theta in this direction, E1 sin theta in downward direction. For this field E2, E2 cos theta in the same direction, E2 sin theta upwards. But minus q plus q, these are the equal charges. Therefore, field strength magnitudes are equal here. Therefore, the horizontal component 2e cos theta are acting in this direction. The vertical components gets cancelled. Due to minus q, the vertical component downward direction. Due to plus q, vertical component upward direction. These gets cancelled. On horizontal components, by combining the resultant value, we are getting 2e cos theta. Okay, so that is I am writing E equatorial or E resultant equals to 2e cos theta. Okay, equation 1, where E is nothing but what? E1 equal to E2 in magnitude. Of course, direction different. E1 bar magnitude, E2 bar magnitudes are equal, right? That equal to how much? That's value 1 by 4 pi epsilon naught q by. If it is L, if it is R, from Pythagoras theorem, the distance of minus q to this point, r square plus L square whole power of. But according to our formula, 1 by 4 pi epsilon naught q by x square. So whole square, you will get r square plus L square. Okay. This is E1 equal to E2. Then we write E equatorial equals to 2 E 1 by 4 pi epsilon naught q by r square plus L square cos theta. Cos theta, you consider this triangle. Cos theta equal adjacent side by hypotenuse, that is how much? L by root of r square plus L square. R square plus L square. This gives 1 by 4 pi epsilon naught q into 2L. Okay, we can write this q into 2L by r square plus L square whole power 3 by 2. Right? But q into 2L gives the dipole moment. This is equal 1 by 4 pi epsilon naught p by r square plus L square whole power 3 by 2. This is the expression for electric field strength on the equatorial line of electric dipole. Again, applying for short dipole, comparing to the r square, L square can be neglected. Since L square very much less than r square, we are neglecting r square. Then you will get E equatorial is equal 1 by 4 pi epsilon naught p by r cube. Okay. So what is the direction of electric field strength on the equatorial line? Okay. If you observe this figure, it is very clear. So what is the direction in this direction? Minus q here, plus q here. This is the dipole axis. What is the direction of p bar? Minus q2 plus q along the dipole axis. But here, at any point on the equatorial line, the direction is like this. It is anti-parallel to p bar. Okay, you should remember that on the dipole axis, the field strength is parallel to p bar. On equatorial line at any point, the field strength is anti-parallel to p bar. That is, we are writing E equatorial bar is anti-parallel to p bar. Okay, coming to the next concept, that is when the electric dipole is placed in the uniform electric field, what is the torque acting on it? Right? Torque, the next concept I am going to discuss is torque acting on a dipole when it is placed in the uniform electric field. For that, consider this diagram. This is the direction of uniform electric field of strength E bar. And now I am placing the electric dipole minus q plus q, right? The length of this dipole is 2L. Okay. Here dipole axis, that is line joining minus q2 plus q. This is the dipole axis, which is making angle theta with the field direction. Okay. We know that when the charge q is placed on the uniform electric field, that can experience the force F is equal to QE. Okay. So when Q is positive, the force direction F is equal to QE parallel to the field direction. When Q is negative, then the force on charge minus Q will be QE opposite to the field direction. Okay. So here on the electric dipole, at two different points, QE here, two equal and opposite parallel forces. Two equal parallel forces are acting in opposite direction. Then the couple or torque acts on it, that will get the rotation. Okay. So due to acting the couple, acting on the dipole, that can be rotated in the uniform electric field. Right. Now the couple acting on the electric dipole is given by any one of the force QE into perpendicular distance between the parallel forces. Perpendicular distance between parallel forces. This is the moment of the couple or torque formula. Torque tau is equals to QE into, so this is one force, it is one force. This would be the perpendicular distance. If it is angle theta here, then in this triangle you consider sine theta. Sine theta equal opposite side, that is the perpendicular distance. Say I am writing it as x by hypotenuse, that is the length of the dipole 2L. X is equal 2L into sine theta. Substitute here, it is 2L into sine theta, equation 1. Okay. So from this, by rearranging that expression, I am writing it as Q into 2L into E sine theta. Tau is equal, but Q into 2L represents what? Dipole moment, capital P, E sine theta. This represents the torque acting on the electric dipole when it is placed in the uniform electric field. So vectorially, we write it as tau bar is equal P bar cross E bar. Tau bar equal P bar cross E bar. That means the torque acts perpendicular to both P bar and E bar direction. The direction of tau bar, which is perpendicular to both P bar as well as E bar. Okay. Of course, here, when the torque will be maximum in this formula, when theta is equals to 0, sine 0, 0, then you will get tau equals to 0. That means, so here dipole, when the dipole is parallel to the field direction, it doesn't experience the torque. When theta equal to 90 degrees, okay, sine 90 equal to 1, then maximum torque acts on the dipole. Tau maximum equal PE, right? That is, when the dipole is perpendicular to the field direction, then it experiences the maximum torque. Accordingly, for different values, theta equal to 30, 60, you can calculate the corresponding torques acting on the dipole. Okay, so this is about torque acting on the electric dipole when it is placed on the in a uniform electric field strength. Right. The next concept is, what is the potential energy? Potential energy or interaction energy. Potential energy of electric dipole placed in a uniform electric field. Uniform electric field. Electric field. Yes. For this, I am considering the diagram. You see this. This is the uniform electric field. So here you can observe the lines of force are parallel and equidistant. The direction of E bar. Okay. Now I am taking minus Q and plus Q. This is electric dipole. Length of the dipole is 2L. That is distance between minus Q and plus Q. Right. According to our previous discussion, on plus Q, F is equal to QE acts parallel to the field. On minus Q, F equal to QE acts opposite to the field direction. Okay. So here, if this angle is theta, that means if the dipole axis making angle theta with the field direction, so then what would be, this will be 2A cos theta. 2A cos theta. Right. So this is the uniform electric field cell. Then if you consider the planes like this, when you consider the vertical planes at different points, that would be equipotential surface. Now I am considering at this position, here the potential is V1. At the position plus Q, the potential is V2. So here the vertical plane passing through minus Q1, equipotential surface V1. Here equipotential surface V2, they are perpendicular to the electric lines of force or field direction. Okay. So then potential difference. At this point minus Q, potential V1, at this point V2 cell. The distance between these 2 points, how much? 2A cos theta. Okay. Then the potential difference, we can write it as V1 minus V2 equal to V equal E into distance between them, that is 2L cos theta. 2L cos theta. This is 2L cos theta. Okay. Say this is equation 1. 2L cos theta. But the potential energy U is given by, that is called, here minus Q charge is placed in the electric potential V1. Then its potential energy minus Q V1. Okay. So here plus Q is kept at the potential V2. Therefore, its potential energy will be QV2. Or in other words, to keep minus Q charge at the potential V1, minus QV1 work is required. To keep the plus Q charge at the potential V2, QV2 is work is required. Okay. So minus QV1 plus QV2. So from that, you can write that equals to Q into V1 minus V2 by taking minus common. Right. So here, say this is equation 2. From these two equations, U is equal minus Q, but V1 minus V2 equal, we have E into 2D 2L cos theta. Substituting that, E 2L cos theta. U is equal Q into 2L, that is dipole moment, capital P E cos theta. This is the potential energy of the electric dipole when it is placed in the uniform electric field. Okay, the potential energy of electric dipole or interaction energy of the dipole when it is kept in the uniform electric field of strength capital E is given by U equal minus P E cos theta. Yes, from this we can extend our discussion that when theta is equal to 0 degree, cos 0 equal to 1, then u is equal minus PE. This is the minimum value. Okay, this is the stable condition. So in this condition, the electric dipole will be the stable condition. When theta equal 180 degree, cos 180 minus 1, then you will get u equal to plus P. This is the maximum value of the potential energy. Okay. When theta equal to 90 degrees, cos 90 is 0, then you will get u equals to 0. Okay. So this is about potential energy, right? So when the dipole has the stable or equilibrium position when theta equals to 0. That means when the dipole axis or dipole is parallel to the field direction, then it has the minimum potential energy. When the dipole is anti-parallel to the field direction, the potential energy is maximum, right? The next concept is, what is the work done in rotating the electric dipole from position theta 1 to theta 2? From position theta 1 to theta 2, right? Same diagram. Yes. So this is uniform electric field. Therefore, the lines of force I am showing parallel and equidistant. In this, I am keeping electric dipole minus Q and plus Q, right? So this is the dipole axis, which is making angle theta with the field direction. Okay. So this is the position of theta 1. Now, my question is, when the dipole is rotating from the position theta 1 to theta 2, initially it is making angle theta 1 with the field direction. So now the work done in rotating the dipole from the position theta 1 to theta 2, that is we have to calculate. So for small displacement, for small angular displacement d theta, the work done is given by dw equal tau into d theta, equation 1. But torque tau is equal what we have PE sine theta, that is derived in the previous discussion. Substituting that, dw equal to PE sine theta into d theta. Okay, say equation 2. Now the total work done in rotating the dipole from the position theta 1 to theta 2 is given by integral of theta 1 to theta 2 dw. Okay, this is equal integral theta 1 to theta 2 PE sine theta d theta. Okay, W equal, writing PE outside, integral theta 1 to theta 2 sine theta d theta. That equals PE integral of sine theta minus cos theta. And I am writing the limits theta 1 to theta 2. Okay. This is equal to PE minus also taken common, applying the limits cos theta 2 minus cos theta 1. Again multiplying P minus into the bracket, we'll get cos theta 1 minus cos theta 2. This is the work done in rotating the electric dipole from the position theta 1 to theta 2 with the field direction. Right. This work done will be stored in the potential energy. Hence, the potential energy of the system in rotation of electric dipole from one position to another position, from one angular position to another angular position, you can use this formula. Yes. So one more point is electric field strength and null point. So actually, that is we have to discuss at the first one. Now I am going to discuss this topic now. Yes. When I consider two equal charges plus Q and plus Q cell. So what is the field strength exactly at midpoint in between them? Suppose it is a distance R, it is a distance R. You can say very simple, due to plus Q, the field direction is in this direction because 1 coulomb charge can be repelled in this direction. Due to this plus q, the field direction is this one. They're equal in magnitude and acting in opposite direction. Therefore, field strength at that midpoint is 0. This is the null point. So when two charges are separated by some distance, or when we consider the system of two charges, the field strength will become 0 exactly at midpoint of the line joining the two charges. Now I am considering the two different charges, q1 and q2, which are separated by the distance r. Here q1 is the smaller charge, q2 is the bigger charge. Okay, q1 less than q2. Right. Suppose, because I consider both are like charges, plus q1 plus q2. Suppose at this point, that is the distance x from smaller charge, the field strength, resultant field strength is 0. So null point position is at the distance x from the smaller charge. Because due to q1, the field direction this one, due to q2 in this direction. Suppose if they are equal in magnitude, obviously at this point, resultant field strength will become 0. So taking that condition, due to q1, the field strength, what is that? 1 by 4 pi epsilon naught q1 by x square. Due to the point charge q2, since it is x, this distance will be r minus x from bigger charge to the point P. This should be equal 1 by 4 pi epsilon naught q2 by r minus x whole square. Let me repeat. Here q1, q2 are at the distance r. The null point P is at the distance r from the smaller charge. Then from bigger charge, distance would be r minus x. So due to this, the field direction towards right side. Due to q2, field direction left side. These are, we are equating. Field strengths we are equating. Okay. From this, you can write q2 by q1 is equal x square by r minus x whole square. Okay. Taking square, root q2 by q1 is equal x by r minus x. R minus x. q2 by q1. q2 by q1 equal to, no, this is q1 by q2 equal to this one, q1 by q2. Then q2 by q1 is equal, q2 by q1 equal r minus x by x. Okay. By simplification, root q2 by q1 equal, right side you can write r by x minus 1. R by x is equal 1 plus root of q2 by q1. Okay. From this, x is equal r by 1 plus r root q2 by q1 plus 1. This is the location of null point from the smaller charge. Okay. The conclusion is, when two charges q1, q2 are at the distance smaller, then the null point position from the smaller charge x is equal to r by root q2 by q1 plus 1. This formula is applicable when the charges are like charges. Okay. Suppose if the charges are unlike charges, then in the similar way you can derive x is equal r by root q2 by q1 minus 1. Okay. You should remember that here q1 is smaller charge, q2 is bigger charge. When the like charges, when we consider the like charges, the null point is, when we consider the like charges, then the null point is forming exactly on the line in between the charges. When they are unlike charges, then the null point is forming outside of the smaller charge at the distance x. So this formula here, x is the distance of null point left side of the smaller charge. So here in the first case, x is equal r by root q2 by q1 plus 1. It is the distance of the null point that is located right side of the smaller charge. This is left side of the smaller charge. Okay. Now, so in this present lecture, in the present discussion, what we covered, the first electric field strength null point position. Of course, we discussed lastly. Then after electric dipole, what is meant by electric dipole? So that is nothing but this is the combination of or the system of two equal and opposite charges separated by some distance. The dipole moment is given by the product of charge and separation between them. Okay. The next, we covered the discussion, the torque acting on the dipole when it is situated in the uniform electric field. So for that, we got the formula tau bar equals to P bar cross E bar, that equal P E sin theta. Next, electric field strength on the dipole axis, we derive the formula E axial equal 1 by 4 pi epsilon naught 2 P by R cube for a short dipole. General formula 1 by 4 pi epsilon naught 2 P R by R square minus L square whole square. Here you should remember that E axial bar is parallel to the dipole momentum vector direction. Next, electric field strength on the equatorial line of electric dipole, we derive the formula. So what we got there, E equatorial equal 1 by 4 pi epsilon naught P by R square plus L square whole power 3 by 2. For a short dipole, E equatorial equal 1 by 4 pi epsilon naught P by R cube. Here the direction of equatorial is parallel to the dipole axis but opposite to the dipole moment to vector. That is, equatorial bar is anti-parallel to the P bar. Okay. After that, we derive the expression for potential energy of the electric dipole, that is U equal minus PE cos theta. Lastly, we derive the formula for when the electric dipole is turned from the angular position theta 1 to theta 2 in the uniform electric field. That formula is W equal PE cos theta 1 minus cos theta 2. Okay, so these are the outcomes of this present lecture. Thank you.